And we'll find Jim in the room here. I do not see him yet. Do you see him, Alan?
No, no.
Oh yeah, James McNay. Yeah. Whoop, he's flying by too fast.
Okay, I'm here finally. Ah.
It's just moving so quickly. 1 second. Oh no, no, he's not there anymore. Oh yeah, perfect. Hi James, can you say something? Can you turn your video on? Jim? Your microphone is muted currently.
Yeah, no, video's not turning on. I'll try. It just won't. Okay, now it is.
Excellent.
All right.
Glad to have you.
Okay, well, we've got everybody here, so I'd like to welcome those. We got 76 attendees already. Absolutely excellent. I'd like to welcome everybody to this special event with BC Geophysical Society, and I'll hand over in a minute to Dom, who'll take over as the moderator. Just want to mention that we have this event today, and then next week we have another EMinar from Haodong on the 16th December at 1300 UT. And then in the new year, Alan Chave on multi-taper spectral analysis, followed by somebody, Joel Janssen, I don't know this guy. Natural source EM methods for mineral exploration. That one should be exciting. Sorry, Joel. And then in February, we have a special invited EMinar from Aliriza Malamar, who was leading smart exploration in the EU. So he'll give us an overview of smart exploration. Just a reminder that you can view all of the previous EMinars. There's a video link and a presentation link and a registration link for upcoming EMinars. And then finally, this is a Zoom webinar rather than a Zoom meeting. And so the controls that most of you attendees have are, you've got the audio settings, you have a chat function, so you can chat to the panelists. You've got a raise hand function. So if you want to speak, raise your hand and we'll see you with a raised hand, and then we can bring you in to speak. And there's a Q&A function. So you just send a Q&A to the presenter who'll speak on the fly or maybe at the end of the presentation. Okay, so at this point, I'll stop sharing and I'll hand over to Dom to take it on.
Thank you, Alan. Thank you very much, and thank you for the audience for tuning in. This is a special BCGS monthly talk. Usually we do it more as Alan said, as a meeting. But thank you for Alan for offering to host us. And so the topic today is regarding the detection of really highly conductive mineral deposits using airborne EM system. And I'm not an expert. Thank you, Dennis Woods, for writing the great summary. I'm sure everyone on the call read the email. I think it summarized it quite well. And to debate this topic, I'm not sure how much debate we'll have, hopefully some. We have our four panelists that are on the call currently. Combined is an amazing experience, decades and decades of airborne EM experience here. So I'll just go present each one of those panelists quickly in order that I currently see them on the Zoom call. So Alan Jones, Professor Alan Jones, who probably has the most experience in the room, studied geophysics in the early 1970s. I was far from being born at that time, and then graduated from Canada, from UFT in the 80s, in 1980. Then 10 years at Lamontagne Geophysics, followed by over a decade at Macquarie University, then 20 years at RMIT University in Melbourne. And obviously countless papers. Jim is a legend, so thank you very much for being with us. Then I have Ben Polzer, graduate from his MSc in 1985, also worked at Lamontagne Geophysics. I'm assuming that you overlapped with
yes.
Jim at some point. And then worked at INCO for 9 years, then Valley for 7, and then principal geo at Novaminex for 7 years. Is that right?
Yeah.
Roughly?
Yes.
Then I have Daryl. Daryl, your LinkedIn account is pretty thin, so unfortunately I don't I don't have too much. But 18 years.
I worked at Lamontagne as well for quite a few years, so I know Ben from there. So
there we go.
The Lamontagne panel here.
Wonderful. That's great. And then yeah, obviously I know you from working at Glencore for 18 years. This is quite impressive career. And then also I know you from UBC, supporting research, always keen to try new things. And then finally, but not least, is Andrew Duncan, also from Australia, graduated from Monash University in 1986, and then also had a very long career and a founder, so a successful geophysicist entrepreneur, founded electromagnetic imaging technology. So to all of you four, thank you very much for taking the time. It is much appreciated. So the format of this meeting is, we hope that we're going to keep it fairly open. So I know that all of you have prepared some slides to show that will take us through this topic, and we hope that we're going to have some exchange. So it doesn't have to be very formal, right? If someone wants to show a slide at some point because it has a burning comment, please do so. And the audience is also welcome to ask questions. We're going to filter through the chat window there, so either Dennis or myself can forward your question. So yeah, maybe without further ado, to get started, I was thinking we could leave the floor to Professor McNay, who I know prepared some excellent slides on with some numerical example to maybe explain a little bit what this whole issue with hyperconductive targets is, and to maybe for non-experts like myself, for sure, to just get us up to speed. So Jim, if you would like to start, I will please let you the floor.
Okay, thanks. Do you see the screen?
Not yet, but it's coming. I think it's just a matter of time. We'll just give it a second here.
My broadband internet is down, so I'm connecting through my phone. It says I'm screen sharing.
In the worst case scenario, I can always broadcast your slides, but let's just give it one more second.
So still nothing.
Still nothing. If you're okay, Jim, I can show your slides, and then you tell me when you want to go forward. How does that sound?
Yep. Okay, sounds good.
Perfect. Can you just stop sharing your screen, and I'll go for it. Beautiful. Okay, I got you here, and I'll go full screen. Where's the full screen on this? I haven't used PowerPoint in a long time. There we go. Can you all see this? You're all good?
Nope.
Yeah, it's fine, Dom.
Jim, are you with us?
I'm with you, but I can't see it at all. Okay, well, anyway, you might as well advance one slide.
Yeah,
And
so I'm slide 1 right now, method 1, if you want to go
Okay.
ahead. Yeah.
Okay, so how do we detect perfect conductors, or PerC for short? Okay, so if we've got a system flying over one, the perfect conductor sees the primary of the transmitter, it gets a current induced with exactly the waveform. And so if you have a receiver, it sees currents in the perfect conductor in the on time only. So there's no response in the off time. There's a change in amplitude and on time. So that's the simplest way. Next slide, thanks. If, however, we stick that target under some conductive cover, PerC, the perfect conductor, sees a delayed primary of the transmitter. You get currents induced similar to the background response rather than exactly the transmitter. Then a receiver will see those currents, and you'll actually get a slightly time-delayed distortion of your background response from a perfect conductor. Okay, next, thanks. And if then we stick this conductor in a sort of conductive host, or say a larger halo response, you get current gathering into it and you'll get bigger responses. Okay, next one, thanks. Okay, so I need to talk a bit about inductive thickness. So first of all, other than squid sensors, there aren't any perfect conductors, and none out in the bush. It's just very conductive things. So we often use conductance, which is the product of conductivity and thickness, to describe these. So if we take something like seawater at the 10 kilometer deep Marianas Trench, we could say that's 50,000 Siemens. Now that's geometrically thick because 10 kilometers is a lot bigger than our system. It's also inductively thick because the skin depth in seawater, which you'll see down at the bottom, which is only up to a few hundred meters, is much less than the sort of the seawater depth. If we have a half a meter of peritite, 100,000 Siemens per meter, that's also 50,000 Siemens. That's geometrically thin because half a meter is small compared to our systems. But it is actually also inductively thick because the skin depth is much less than the width. So if we, in peritite, at 10 kilohertz, we've got something like a less than 2 centimeter skin depth. Okay, next slide, thanks. So this is just a section through a thickish conductor of how skin depth gets into a very good conductor at very high frequencies. At the top left, we've got a skin depth of say 2% of the width of the conductor. We're only actually energizing 5% of the total conductance. So you get the whole conductor's not responding. As the skin depth increases, you get more and more of the conductor responding. And until the skin depth exceeds the actual conductor thickness, you don't get a full estimate of how conductive it is. Okay, next, thanks. Okay, here we're looking at some old frequency domain maximum data over Gertrude West. And in frequency domain, when they changed the frequency, they came up with a different estimate of the conductance. So it appeared to look, if you look at the top right-hand side, it appeared to be more and more conductive as you lowered frequency. And using the inductive thickness model, I calculated what the response looks like, what apparent conductance you'd get as a function of frequency, and that plot's on the left. So for something like a 1 Siemens conductor, you always end up with 1 Siemens. The 200-foot slingram data has got about the same slope. Some of my more conductive things doesn't quite fit. But effective inductor thickness and frequency domain on something like a conductor means you get apparent conductances a lot less than true conductances, even at quite low frequencies. Okay, next slide, thanks. So if we come to time domain, this is just a 50% duty cycle square wave. And I've just calculated some decays of a thin-ish body, geometrically thin, with inductive thickness. So that's what the response looks like. It's got different responses in on and off time as a function of conductance from 1 to 10 million Siemens. So that's pretty conductive at the top end. Okay, next slide. And if we plot the response in log amplitude versus log time, if we look at the off time decays, you can see they decay quite quickly at 1 Siemens, which is the blue one on the left. Moving red is 10 Siemens, yellowish 100 Siemens, then 1,000 up at the top. Then the response drops off, but all of those decays actually look pretty similar in shape. The on-time decays are somewhat different in the sense their amplitude doesn't drop off. They just saturate up at the inductive limit and stay up there. But this is a log plot, so there is some sort of detail in the decay that you can't see. Okay, next slide again, thanks. Okay, in this, I'm hoping you've got the version which shows some slope. If you go 1 forward, do you see slope 1? Okay. If you plot log amplitude versus linear time and fit a straight line to a measured decay with an exponential decay, it'll fit a whole batch of points. So if something has inductive thickness, we fit the last 2 points, we can come up with a time constant. And if you click the next one, between the next 2 points, you'd get a steeper slope, which means a shorter estimate of time constants, etc., etc. So the equivalent in time domain is that you never stabilize with a conductive estimate. So, but you can always use the last 2 channels above noise or numerical noise to estimate conductance. And on the next slide, I've done this in a table. So if you look at the middle of the table, okay, this is a 10-meter wide conductor. We've got 100 meter sort of geometry size, 1 hertz base frequency. The true conductances are going from 1 to 10 million. If we use the last 2 channels in the off time, we get 1755, 307, sort of close or slight underestimates. But once we get above a few thousand Siemens, we get pretty much the same number. That's sort of the perfect conductor that you just can't, with off-time data, tell how conductive it is. If we actually use on-time data, so we've got a good enough system that we can extract on-time data, we actually get slopes that correspond to much greater conductances than you get in off-time. So, okay, so next. So how can we tell these fantastically good conductors if they're in free space, no cover? The longest tau you get is similar to the base period. There's one symptom. That estimated tau increases with delay times. If you estimate it on different channels, you get sort of different amounts. And if you're using off-time data, there's a limit as to how conductive you can actually get. So in fact, on-time decays are much better than off-time, even if geometry is uncertain. You can get those if you've got streaming receivers and a current monitor or a very good system. Okay, next slide, thanks. Okay, so I'm not going to have time to discuss the effect of cover, but that can falsely give much the same impression as the symptoms I was describing of inductive thickness. But most 2D and 3D algorithms, if you're running 3D models in the literature, they don't account for inductive thickness because the voxels are too big. You actually need things like 2 centimeter voxels in peritite at 10 kilohertz. Can we use DBDT? I'll say no, I'll just skip that. And I'd just like to get on to a field example using the Armit B field sensor. So that's 2 slides ahead. This is run with slinggram geometry. So we've got 300-meter loops with a receiver 300 meters off. Got a profile in the middle across this. Because there is a over 100 Siemens of conductive cover, you don't actually start to see the response till after about 10 milliseconds of decay. And this particular response is a 300 by 150 meter conductor, roughly 220 meters deep. It's been drilled and confirmed to be pyrrhotite, very conductive pyrrhotite. And the top right, if we fit a sort of log amplitude, linear time, straight line to it, we can see that the slopes are increasing as we move away. So that this has got all the symptoms of inductive thickness. So that would be an example of that. Okay, so if we go to the last slide, thanks to Nick Ebner for the Armit data, which was measuring B fields, and Sandfire, who gave permission to use it, and the seminar organizers and people who helped with Armit. Okay, that's it. Thanks.
Thank you very much. That was perfect introduction. As I was preparing for this talk, I stumbled upon one of your paper that you wrote earlier, I think 2007, about the Gemini project. I don't know if you probably, I'm sure you recall.
Yeah.
You had a really interesting quote in there, and you said that the success of airborne systems at detecting mineral deposits might have been somewhat of a serendipitous, because actually the good conductors were probably not well detected, but only the surrounding. And I thought that was pretty funny. Speaking to this, I think Daryl will show us probably an example that speaks fairly well to this statement. I'm sure you might think now that you've been somewhat lucky at some point, Daryl, in your exploration program, where you found something that was too conductive.
It's always too conductive.
So yeah, go ahead if you would like to show your presentation. That would be the perfect time.
You see it there? Can you see my screen?
Yeah.
You're good to go. Yeah.
Okay, good. Yeah, I'd just like to thank PerC, because they are a joint venture partner with us on the Kabanga project, and they gave us permission to show some of this data. And I'm just going to go over physical properties and look at some airborne surveys, some ground surveys, and then some conclusions. I just started my timer. So this is actually data from Raglan, and it shows these are some physical property probes. So we're looking at total gamma, magnetic susceptibility, and then conductivity. And in the zones down here where all the nickel is, you can see that it basically goes from 0 to quite high conductance in this area. It's probably about 100,000 Siemens in both these zones. But you can see on this particular slide, there's some disseminated sulfides here. So there's a bit of elevated conductivity here. But once you get into the massive sulfides, it's just like going from night to day. And you can also measure the conductivity with some tools that are available. This one's the KT10 and KT20 that you can get from TerraPlus. We've taken over about 500,000 readings at Raglan with these tools. And here's a picture of the problem. And you can see on the right-hand side how conductive the nickel sulfides are. And typically everything below 1,000 meters here is where everything else resides. We're sort of up on our own with the nickel problem. So this is the Kabanga North deposit here in the Temple. This was a new discovery that Falconbridge made when we were working on the property, and it gets quite deep down here at the bottom. But for most typical airborne surveys, you're not going to see much below 400 meters here. So I just cut it off at 400 meters, and and just flew the helicopter over the deposit there. So one survey that was flown before we got there was GeoTEM, and you can see the conductance here on this slide. So we're trying to measure something that's over here on the right-hand side of the screen, which is getting quite close to the noise levels. And this is the GeoTEM survey. It's 400-meter survey lines over the Tembo and the Kabanga North deposit here. And you can see that there's some, this is the late time B field channels. And you can see there that the GeoTEM survey, it's really state of the art at the time, but it didn't really pick up this deposit at all. So it was blind to it. And when we were there in, I think this is circa 2008, we flew a VTEM survey over the same area, and we got similar results here with this is lake time B field. And once again, you can see that there might be something that's showing a little bit elevated conductivity over on this side, but it was blind to the Tembo deposit here and to Kabanga North there. You might say that there's a bit of a response here, but it's, you know, when you're picking your targets here with this survey, would you actually, you know, pick this over this anomaly here? Then once we got to the ground, we started doing some ground surveys. The first thing we did was a squid survey. This isn't Tanzania, but it's Raglan. And these are the results over Kabanga North. This is actually a 200 meter by 200 meter moving loop survey with the receiver on two lines, two stations per line. And you can see that there's the red HZs, we're getting a positive response, and a crossover on the HX. And the moving loop survey goes all the way up about halfway to the top of the screen there. And then we also did, after that, we did some UTEM and some Crone surveys. And you can see there's quite a nice crossover here on the Z component and a peak on the HX here, which lines up quite nicely with the Tembo. So here it's down about 100 meters below surface, and it gets a little bit deeper over here. But quite nice, nicely resolving the data. And I blew it up here just to take a closer look at it. You can see how the HX crosses over the white lines here, which are the survey lines, and a really good corresponding crossover. And this is just the latest time response here. And then the next slide brings in the decaying response. And you can see with the decaying response, we're actually picking up something that's more aligned with this sedimentary conductor over here. And you can see that we're missing all the nickel on this side. And then we'll go back to Raglan here. This is a AeroTEM survey. This is the Donaldson head frame here, but the VTEM, or sorry, the AeroTEM measures both in the on time and in the off time. And if you look at some of the results over at Raglan here, you can see these are all a bunch of near surface deposits, lenses, and you can see in most cases the late time AeroTEM responses here do pick up the nickel sulfides. They're also picking up the conductive sediments over here. And then we also do regularly do borehole EM surveys. And I've got this quote from 2002, and it appears that the mineralization here is exceptionally conductive, giving rise to unconventional downhole EM responses that are difficult to model with conventional plate modeling software. The effectiveness of analyzing the ramp response in this environment concluded that more information is present in the off time than the data in the ramp time, but that's actually where all the information is. It's in the ramp time. And this is also at Raglan, so it's this is a discovery hole that we drilled, finding a model on this plate here. Nice off-hole response pointing in this direction, and we followed that up, and You can see when you're measuring the off time here, you get the nice positive response on both sides where it's missing, and then the in-hole response is these purple lines. And you can also see that the decaying response here is a bunch of weaker conductors above the deposit. So this turned out to be a 3.2 million ton lens at Raglan. We're just underway to start mining that right now. So my basic takedowns are you got to know and understand your physical properties, because you are looking for something that's quite conductive. You should always, it's always nice to have a test survey to fly over a known target or a ground target if possible. That's not always the case, but you got to remember that the nickel sulfides in these Archean rocks are the same in Raglan, they're the same in Thompson, and the same in Australia, same in Africa. They're very conductive, and you have to use the right methods to survey for them. And that's me. I've got another 2 minutes.
Thank you very much, Errol. That was great.
Okay.
Would Andrew or Ben would like to follow with their analysis? Andrew, why don't we'll start with you.
Yeah, okay. You can hear me okay?
Yes.
How's that?
You're good to go.
Okay. Well, good morning to you if you're in my part of the world, good evening to the Americas. I'm going to talk along the same lines as what Jim and Daryl talked about, and I believe Ben's going to talk about a model study in highly conductive targets as well. I'm going to follow on from some of the model studies I presented in an Exploration 17 paper. And in that I was using a 3D slab model to compute 50% duty cycle, 100% duty cycle, and late time normalized 100% duty cycle responses from conductive targets. And in this presentation, I'm going to limit myself to 100,000 Siemens per meter targets of various thicknesses. And clearly the important issues for us to talk about are detection and discrimination. So as I mentioned, 100,000 Siemens per meter, and so we're talking about n-member conductivities here where there's really no conductive halo absent, with no conductive halo present, sorry. For simplicity, I'm going to use a fairly arbitrary model, but the key issues here are what happens when you do different things with the transmitter waveform and different processing with the receiver waveform. And I'm going to calculate B field responses here for 0.1 Hertz and 1 Hertz transmitter waveforms at 50 and 100% duty cycle with some logarithmically spaced time windows. So the arbitrary kind of model that I've put together here is has a 400 meter diameter circular transmitter loop. It's a cylindrical symmetry, as I mentioned before. Measuring the vertical component responses at 750 meters depth. Let's see if I can. If you can probably, you might be able to see my pointer there. That's the receiver position, 750 meters below the transmitter. The target is a 300 meter diameter disc of various thicknesses, conductivity 100,000 Siemens per meter, and it's 1 kilometer below the transmitter loop. So it's 250 meters below the calculated receiver position. I'm going to calculate on time 50%, off time 50%. 100% duty cycle measurements and late time normalized 100% duty cycle B field measurements, where the signal during this time is normalized by the latest time. So the conventional sort of presentation of decaying 100% duty cycle responses. A couple of things by way of introduction. This was a slide from my Exploration 17 presentation where I estimated the current flow, or calculated the current flow in an ovoid model at the latest time in a 0.1 Hertz 100% duty cycle survey. So the ovoid model is 100 meters thick, 200 meters diameter disc of conductivity 100,000 Siemens per meter. So this is a 10 million Siemens conductor. This is really N member kind of stuff. And you can see there at the latest time, so that's 5 seconds after the transmitter switch. The currents haven't penetrated very much into this 100,000 Siemens per meter conductor. But they're kind of hanging around the corners there, and they haven't gone in too far. Also by way of introduction, it's kind of interesting to think about at what time in a TDEM survey the TDEM behaviour becomes late time. In other words, at what time is the eddy current, is the current donut sitting in the middle of the target and decaying away in place with a characteristic late time decay constant. When you do the calculations, and these calculations are from Gallagher, Ward, Home. I can't see the date there, but that's the calculations here based on a 300 by 300 meter conductor of 100,000 Siemens per meter and variable thickness. And it turns out that if you're surveying at 1 hertz over this target, then if your conductor is any thicker than 0.1 of a meter, in other words, 10 centimeters, then you haven't reached late time behavior. For 30 hertz, old-fashioned EM, we're down below, we're around, we're out there, less than a centimeter. 0.1 hertz, any target bigger than 1 meter, thicker than 1 meter, sorry, we're not getting near late time behavior. These are based on theoretical calculations from a thin sheet model and DBDT responses, by the way. But this gives you an indication of the importance of thickness here, inductive thickness, if you like, and the kind of imbalance between the inductive thickness of these very nice targets and the surveys at which we do TDEM. A little bit of a disconnect there. So let's get on to the modelling responses. I might just go through this fairly quickly because I might have more than 10 minutes of material here. So as I mentioned, 100,000 Siemens per metre, and this is a 1 metre thick target. This is a comparison of, and you'll see the colours there at the bottom of that decay plot. It's a comparison of 100% duty cycle response, a late time normalised 100% duty cycle response in black, 50% on-time response in red, and a 50% off-time response in blue. And I've got a 0.1 hertz measurement there and a 1 hertz measurement. So you can see a demonstrable increase in signal size by dropping the transmitter frequency. So if you compare the decays with the cross of one colour and to the decays with the circle in the same colour, you'll see, regardless of the style of measurement, you increase the response by dropping the transmitter frequency. Increasing the thickness by a factor of 3, so the same conductivity but 3 times the thickness, 3 metres thick, 300,000 Siemens target here. It's the same target. You're starting to see the pure on-time measurements creating a distinct class of signals that are higher than the 100% normalised, the late time normalised 100% data and the off-time data in blue. And if we go to 1 million Siemens, this is now a 10 metre thick, 100,000 Siemens per metre target. There's a much bigger distinction between the on-time and off-time normalised responses. But there's a reminder here that you can't measure these on-time responses. So this is the 100% and 50% on-time responses. You can't measure this without some knowledge of the primary field. So you know the amplitude of these responses to within the error at which you're measuring the primary field, which is really a source of noise at those times. You can, of course, achieve or get hold of the late time normalised 100% duty cycle data and the 50% off time normalised data. And of course, you can measure the late time 100% or 50% on time measurements to within the scope the accuracy of the measurement of your primary field. So this is it's folly somewhat for me to put these on this plot, but it gives you an indication of what's happening in the on time with much bigger signals. This is a comparison at 0.1 hertz only of those three targets, so 100,000 Siemens to 1 million Siemens, and you can see that. So we're comparing, for those four measurement styles here, we're comparing perhaps the ability to discriminate those targets. And Jim was talking about discriminating these highly conductive targets based on their inductive thickness. This supports that argument. I think you're still seeing variations in these decay shapes, and this is at 0.1 hertz. So at that kind of frequency and at these kind of conductances, TDEM does have the ability to discriminate these targets, and clearly the best technique for discrimination is going to depend on the signal to noise of the measurement technique we're using. So we need to talk about signal and noise here. Just for fun, I modelled an overburden of 100 Siemens on top of that target. So this overburden is 100 metres thick times 1 Siemens per metre. So that's 100 Siemens. That's its surface. So the transmitter loop is basically sitting on top of it. In this particular case, with this 1 million Siemens conductor down 1 kilometre, the response is asymptoted to the target response at around 200 milliseconds, and that was really regardless of the type of field calculation. And really, I only put this in here as an indicator of why would you be measuring at very low frequencies, and this is the sort of thing that's driving it. So clearly the TDEM signals in the on time are larger than the off time, assuming the same transmitter current by an amount that's dependent on the target itself and the transmitter frequency. As you go to lower transmitter frequency, like 0.1 hertz here, on time and off time responses become close. They can become closer together for all but the most very conductive large targets, which are the nice ones that you'd like to find. Late time normalized 100% duty cycle responses are around the same as 50% off time responses at the latest times, and I think that's very important. For an extremely good conductor like the ones that are presented here, there's not much difference between the on-time response from a 50% duty cycle waveform and the on-time response from a 100% duty cycle waveform, which I think is kind of interesting, and may lead to you thinking about things like doing your survey at 50% and extracting both. So how about the other part of the equation, which is noise, and I think this is sometimes overlooked or ignored. Generally, the noise in an off-time measurement is a result of either sensor noise or external noise factors. And as an aside, these issues can both be addressed by increasing transmitter power, and that's perhaps a summary of how things have gone in my part of the world. In an on-time survey, the biggest source of noise arguably is the primary field, and the secondary field is riding on top of that. If you're measuring a long distance from the transmitter loop, then that may not be the case. But the primary field, which is large, needs to be estimated somehow, either by measuring the geometry of the survey or deal with it in a manner like normalizing by the late time response. And that leaves you with what is not really on-time data, but leaves you with something that is a pretty good result anyway. Interestingly, increasing the transmitter power doesn't help you with those issues. Now, the other issue in an on-time survey, and depending on the type of equipment that you've got, is that variations in the current, either by design or not, if they're significant, and they usually are, then they need to be measured and corrected for. Otherwise, they're just another source of noise in general, and there's not much you're going to be able to do about that unless you measure it and correct for it. So I've been talking about end member conductors here. So they really are special cases, and targets that we perhaps more often deal with day to day are not so difficult to see in the off time at these kind of low frequencies. I think a full understanding of how these things respond and the noise sources is pretty important, because this is a signal to noise issue, not just a signal issue. If you don't use a full 3D model to try and understand these inductively thick responses, then you really don't have the whole equation going on here. So analysing the noise in the survey is important if you want to understand the optimal way to detect it, and part of that can be calculating what the primary field is and what kind of impact that's going to have on any kind of analysis you're going to do. I really have to say that low noise mags and low frequency surveys, in other words, low transmitter frequencies, have changed the way that these really conductive targets are being discovered, and I'm not just talking about here or in Canada, but both of those are true, but everywhere. And as I said, I think it's important to model and estimate the signal to noise in a survey, and it can mean simple things like reviewing the noise of different survey styles and in physically the same units, because otherwise you're not comparing apples and apples. Thanks very much to BCGS-MTNet and the other presenters and EMiC, and I think that's all I had to say. I might have come in at roughly 10 minutes maybe.
Thank you very much, Andrew. That's great. Before we move on to give the floor to Ben, maybe I would like to ask two questions that are related, coming from the audience, and it has to do with either using the B field or DBDT to either for interpretation, for direct picking, or for inversion. I don't know if the panelists would like to weigh on this topic, if one is more valuable than the other, or if you were more successful with B versus DBDT. Andrew, maybe with just in terms of noise, you think it doesn't matter?
I think so your question was what DBDT or B is the well, it's all coming down to signal to noise. So the conventional, I think I'd be right in saying that conventional TDEM started as a kind of rectangular transmitter waveform with a coil sensor. So we're measuring DBDT, and it was typically done at fairly high frequencies, and the coil sensors had good signal to noise at those high frequencies. When things moved on and people realised the signal to noise issues that were inherent in that style of measurement, then I guess we got towards the development of magnetometer systems, and transmitter frequencies started to get lower and lower. I'm talking about in the last few decades, and it's horses for courses, really. So that it's pretty simple to calculate the signal to noise for a particular type of system and a particular type of target. Very target dependent. For these very very conductive targets, there's probably not much point in a conventional approach. I think it's pretty safe to say that. Perhaps one of the other guys could address this.
Yeah, I could comment there as well. Simply that it's a little more complicated, that they're not necessarily pure B and pure DBDT systems. The system I've been working with over the last many years is kind of in between, because the coil has a wacky transfer function. It doesn't have a nice tidy transfer function that is an exact dB. It's dB/dt below 0.1 hertz, and it's B between 1 hertz and 10 kilohertz, and then it's something else. So as Andrew said, it really, within any spectral band, it really comes down to signal to noise. And part of that noise, if you want to call it that, is if you don't have a system with the perfect response is fixing that and putting it right. Deconvolving it is, and the limits of that process are part of can contribute noise as well. So there's certainly a desire to have a pure B and or pure DBBD system that don't need that. But in practice, some level of deconvolution can pollute the pool.
Daryl, any comments?
It's basically the same for DBDT. It's more low frequency surveys if you're looking for zinc or something like that. But for us, we tend to use a B field sensor for the highly conductive stuff, and we can measure 3 components at once. And in the case of the system we're using at Raglan right now.
Yep, Daryl, just for the uninitiated, 2 of the sensors that we use all the time, and you do too, the flux gate and Lamontagne. They're both B sensors pretty well, and they're one is almost 100 times noisier. They're 50 times noisier than the other. So just because it's B doesn't mean it's it tends to, yeah. Anyway, just wanted to make that point.
Okay.
And Jim, if you wanted to weigh in, otherwise we can give the floor to Ben and you can present your talk. Jim?
I think everything's been said, so we can keep going.
Very well. Ben, the floor is yours. Your microphone is still muted, Ben. I will unmute you.
There we go.
There you
Okay,
go.
great. The little button got hidden. Okay, am I good there? Okay.
You're good to go, yeah.
Okay, so thank you, Andrew, for introducing a lot of what I want to talk about, and I agree with almost everything you say but one thing, but maybe I misunderstood it. I'm going to talk about signal and noise, and although we talk about measuring with an on-time or off-time system, but we don't measure just the field that we're interested in. We have noise polluting what we're measuring. And the detectability actually depends on the signal to noise ratio. It turns out that on-time systems, as Andrew also pointed out, can be more vulnerable to certain types of systematic noise. And so it's really interesting to see how these interplay, because maybe there is a role for off-time systems after all. Where I'm not sure that I might disagree is that I'm using an extremely simple model, and I think this is quite useful because it represents the primary late time inductive eddy. This is just from Grant and West, a simple RL circuit, wire loop in the ground with a transmitter and receiver. And I'm not going to go through the development because it's in the EM chapter, but ultimately in the lower right here. In the middle here, you get the magnetic field at the receiver for a step-on current, and the dB by dt, the rate of change of that here. And both of these have a basic, e to the minus t over tau form, whereas the initial amplitude for the single transient is inversely proportional to tau. Now, of course, in the real world, we can't just measure from a single step on, and we have these various waveform and sampling schemes. 3 basic ones I'm going to talk about here. It's basically a 50% duty cycle measuring in the off time, 50% duty cycle measuring in the on time, and 100% duty cycle measuring. And that transient magnetic field that we saw there, of course, in practice, we can't just have with an infinite train of waveforms. At our time gates here, we're measuring an infinite series of overlapping responses. As the tau for the conductor gets much longer than the period, they all start bunching up and overlapping. We're measuring a cacophony of these things overlapping here. And so the interesting thing, the reason this model is really good is that because it's a simple exponential, you can sum the series of all these decays, plus, minus, and the pattern of pluses and minuses is different for the three different types of decay, waveform sampling, of channel sampling. With a little bit of manipulation, you can basically rewrite this and you can pull out the exponential, the original exponential term, times this infinite series, which can be summed by a simple identity into this form. So what you have is you have the original transient that you would have for a single step and its behavior vis-a-vis the dB by dt times a periodicity factor. So there are three different periodicity factors for the three different, I didn't write them down here anywhere. The one here is for, anyway, there are three of the different factors. And so they have different behaviors as a function of tau over the period. So when the time constant of the conductor is equal to the period, you're in here. And these are just these multiplicative factors. So for a 100% duty cycle on time, it starts out at 1 for a weak conductor. And as the conductor gets stronger, it starts dropping, and then it levels off at 50%. If you measure in the on time, I checked this a couple times, but I might have made a mistake. I don't think so. On the on time, it actually starts rising a bit and then settles back down to 1 again. That's because the first, when you're measuring in the on time, this is an up pulse, and the first one is from behind is an up as well. It emphasizes rather than this one being a down and this one being an up canceling. So anyway, you have these three different effects. And of course, this is what we see with dB by dt systems. We see a 1 over tau discrimination against good conductors coming from the periodic, from the periodicity factor. And we already had the 1 over tau from the original dB by dt. So we have a 1 over tau squared behavior for dB by dt. And we have this kind of more steady behavior for pure on time. And as Andrew pointed out, for late time, although it's not done here, for late referenced on time, we have a 1 over tau behavior as well. So how are on-time measurements done? We've already talked about this. I'm not going to waste a lot of time. You measure a waveform that's not perfect. You do some deconvolution. What's left over, you call the anomalous signal, relative not to 0, but relative to some level. And if this red curve is the actual primary field, then we actually have this is the decay. The anomalous field is the yellow part, the difference from the primary field. But if we don't have this magic knowledge of the actual primary field, we can compute the primary field with the green curve here with all our knowledge of how things are pointing and how they're calibrated. And we get an error here, and that's the geometric error, or it also can be magnetostatic. I'll talk about that a little bit. And then the third way is just to throw up your hands and say, well, we're just going to assume everything's decayed away and call the end, and this is the transient. The point is that this looks like a bad estimate, but it doesn't mean that we have it wrong as long as we do the same thing in any inversion program or modeling program or whatever that we're comparing to. It's fair game. It's not strictly error. It's in order to study noise and signal, I'm going to use that basic model, that basic current element ribbon, and because it's so simple and so fast and everything else. And here's an example. I don't have the parameters here. It doesn't really matter. The whole point here is that this top one is expressed in picotesla per amp, and the bottom one is expressed in percent of HT, of total local total field. And the reason it's useful to express them in two different ways, there are lots of exploration reasons for that, but from a signal to noise point of view, is some noise that's systematic tracks the primary field. So it's easier to account for it when you're looking at data that's normalized in the percent of primary field, and some noise is absolute, and it's better to look at absolute signals. So what are the sources of noise? So the on-time system is much more sensitive to a long tau in theory, and Andrew really pointed this out. But there are a bunch of things that get in the way. There's this fidelity of the waveform. That's basically not the accuracy of it, but how well you can predict its shape, its spectral content. In instrumentation, in my experience at least, 0.1% is pretty easy to do, really easy. 0.01 is hard, and to 0.001 is really takes a lot of doing. So magnetostatics cause what I call noise. It's not really, it just means that just as the Earth's magnetic field is modulated by the magnetic minerals in the rocks, so is the field of the loop. And so it tends to amplify and so if you're in an area with 500 nanotesla mag anomalies, you might expect 1% variation in your primary field residualized results. And then there's stochastic noise, and I'm going to talk about system noise and vibration noise. So this is just a spectral density function from a sensor of a system that we use here in Sudbury. And although this isn't taken from Sudbury, you can tell because there's only 150 hertz spike here for the power line. And being able to collect time series and look at the noise up close in terms of a spectrogram or a spectral density function is super important. But one of the cases I'm going to make here, which is something I wanted to kind of take further for this talk, but I didn't get to, is to basically show how it might be used. An interesting question, and this also, an interesting question is, how does this noise affect the dropping of the tendency for systems to be dropping their base frequency? And Jim McNay wrote a paper in 1984 where he described how to take a spectral density function, which is what MT guys are used to looking at, and how to turn that into estimates of samples that we do with time domain EM. So if you were measuring 5 minutes per station at 1 hertz, what do you expect the standard deviation to be? You can get estimates with the techniques described in Jim's paper. And although I wanted this to be real, and it's not, it's a cartoon, I suspect what's going to happen is 2 things. First of all, when you look at data collected with real systems in the field, back here, you see that the kind of the natural field spectrum tends to go more like this. Usually about 10 hertz, you start to get some kind of a break happening, kind of a dog leg upward. That's vibration noise. And in this particular case, the tripod has a resonance at 35 hertz. This little spike is also vibration noise. So what happens is that what you're interested in is not necessarily just maximizing the signal. The lower in base frequency you go, the target signal will increase and increase and increase, as we've all talked about. But the noise eventually is going to hit this hockey stick, and the vibration noise is going to take off. So if you actually plot the signal to noise, you're going to end up with some kind of an optimum. And so in terms of survey design, what's really important is to know in your environment, whether it's blowing snow in the Arctic or on muskeg where you can't keep your tripod steady at 0.1 hertz, or is just to go collect some time series data. You don't even have to have the loop running. And you'll be able to do predictions about where the sweet spot is. Is it worth going to 0.1 hertz or not? You might be better off bringing it up higher. So with some knowledge of noise, I haven't really gone into much, and that model, then you can do play a little game. For any given model, for instance, a 100 by 100 conductor, a certain dip, a certain sigma t, and a certain base frequency, you can basically compute all the responses over an entire grid for each of an ensemble of plate locations. And then you can plot for every imaginary survey that you've done, you can take the maximum response and you can compare it to the noise level that your noise analysis has tagged on the system. And then you can use contours of these images to put limits of depth of investigation. So here's this process taken to its conclusion for one example that I got going this afternoon. And then I turned the crank to run a whole bunch of others because I wanted to do a model study. And all of a sudden the results didn't look so good. I kind of believe these, but I think there's a problem with this. Like, this is good enough to show the principle, but I can't really show the model study. If anyone's interested, because I'm going to get this fixed at some point and do a little study on this with a range of parameters, or has some suggestions about what range of parameters I should run, then send me an email and I'll send it to you when I get it done. But the point here is this. Each of these points on this plot, actually I didn't have the plot, is the location of a 45-degree dipping 100 by 100 meter 10,000 Siemens plate. And so for every square on this thing, the plate's been run and the whole profile's been run with a loop running from -1,000 to 0 to -1,000. So it's in the loop on the left and out of the loop on the right. And the colors denote the maximum response, and the kind of, thinking is that if the maximum response exceeds the noise, then you're going to see it. If it doesn't, you're not. So this is the first plot here is the latest channel normalized by the primary field. So this is the old channel 1 in UTEM language. And I've never been able to get the geometric noise and magnetostatic noise down below 2%. So basically, this is a log plot, and so 2% is, is just above the 0 there, that orange. And so the 2% line is here. So everything above that line, you can detect. You'll be able to detect that thing above that line. But of course, the difference channels, the late time normalized channels we have as well. And those are shown here. But the late time normalized channels, they're not noise free. Of course, they have, here they're normalized by the primary. And so in terms of percent of primary field, there's still the case, the case of fidelity of the system and the deconvolution and everything else. So if you can only do that to within 1%, then even the off time, those channels will, typically we can get to about 0.01%. As I said, it's hard, but you can do that between 0.1 and 0.01%. So if you imagine the line in here, everything above there is in the detectability zone. And then finally, you have to analyze it from a non-systematic point of view, from the absolute point of view, in raw, plotting this data the same way, the same data, but plotting it raw as picotesla per amps here. Then I know for this system and in this environment or whatever, I can get, roughly 10 to 15 femtotesla per amp. Then somewhere in here, I can see an awful lot. I can, I've pretty much covered the bases down to 500 meters here. So what I propose to do here is to do this for a lot more cases and come to some conclusions, and I didn't manage to do that. So my conclusion is that it's possible to use simple models for induction that, in this case, the simple ribbon model, it's even simpler than that. There's a bit of a fudge so that you can put conductance in and get something that's kind of close. It doesn't really matter if you're speaking the language of, you only care about the tau relative to the period. The conductance doesn't matter what the absolute conductance is exactly. This does not account for things like inductive thickness or decay around the fringes or anything like that that might betray a conductor in reality. But this is more to cover the cases of a conductor far away where you only see the dominant mode geometrically, the big circulation around the center. When you combine the signal to noise, I think this could be taken a lot further, of course, and the combination of knowing your noise sources from time series of your data and processing it in some way like this, I think is pretty, has a lot of promise. Do I have time for an appeal?
Let's open the floor, yeah.
I thought I would get hooked by now, dragged off. So the off-time practitioners, this doesn't directly relate to the talk, but I thought about doing a lot of other things. And this, pay heed to the base frequencies that are too low. I mentioned that. And the on-time recording. Sorry, I got this in reverse order here. Getting some, Andrew, you spoke about this as well, getting some on-time recording into a system that's purely off-time would be huge. Doesn't have to necessarily be really fancy. Look at Bill Ravenhurst. That technique of his is really, really nice, although he had a really accurate ramp to help him out in his system, right? Think about taking an on-time transmitter and just busying up parts of the on-time, it doesn't have to be that accurate necessarily to add a lot, because I'm going to go to this. Sorry, the ovoid. This is the case that that you were modeling. Of course, the ovoid, the overburden is only like 30 meters thick, and nothing's conductive around here. And you're right at surface. And with an off-time system, I'm not going to go to the description of this, but just to say that these are two on-time systems, and they both say that they're, for the uninitiated, this is a UTEM and this is a helicopter EM, that there's something, this says a lot more, of course, that there's something really conductive right near surface, right there, and you're right on top of it. And this one says not much of anything at all. This is geotem, just a little bit of a weird wiggle. So those are my appeals, and that's my presentation.
Thank you, Ben. That's great. I guess we can kind of like go back a little bit and think in terms of modeling, right? So we talked about trying to figure out, first of all, can we detect the anomaly? And then after this, we're trying to figure out, maybe what's the conductance of the bodies. What is the significance of this, right? To make the difference, let's say, between 100,000 to 200,000 Siemens per meter. Does that give us any information about the mineralogy or the shape, or what is, other than just pure detection, can we get any extra information out of this?
I guess the question is, if you don't see that 100,000 Siemens conductor, like the example I showed you, there's a risk of missing it altogether, and the same thing with the ovoid, right?
So it's not so much about the differentiation, but straight up detection. Yeah.
So once you don't really see much between 100 and 200,000 Siemens when you're actually measuring the physical properties. I think at Raglan, we're up around 100,000. We did get up to about 160,000 at Kabanga, but typically, if you can see at 100,000, it's not going to make much difference anything beyond that.
You just end up in saturation level past 100,000. I see. Yeah. There was another question also that was interesting. If they were anywhere in the world, other than, I guess, sorry, not just the world, but in terms of type of minerals than the nickel sulfides, is there any other geological context that we could encounter something that conductive? Because we talked mostly about nickel sulfides, but
there's also the problem with conductive sediments, and they can have similar conductances to nickel. And in one instance at Sudbury or in Raglan, we had some 100,000 Siemens sedimentary sulfides. They were laying right on top of the ore, and you're basically blind at that point, because if you can't differentiate between the two, you're in real trouble.
There's a huge difference in different camps. Like in Sudbury, for instance, almost anything that lights up is going to put some kind of a smile on your face. And to your point, Daryl, in Thompson, there's a lot of sulfides right next to the nickel-bearing sulfides that are totally barren. And in a lot of environments, that's there for geological reasons. It's because the reason the sulfide nickel deposits are there as they scavenge sulfur from an in situ sulfidic source as the magmas came through. And so a lot of times you find, so I mean, that's a secondary thing. We have to find things to drill them. In the end, only the drill can can differentiate between those two.
Andrew, you wanted to say anything, add anything else, or Jim?
I was gonna say in that, as I understand it, I think if you're looking at 100,000 semen target or more, then there's going to be some level of interest in most places. It sounds like there's some rubbish conductors that can approach that. So those are big numbers, and that's pretty conductive. Yeah.
So it would be worth investigating regardless.
Well, it's not strictly from the discrimination point of view, but really from the detectability point of view. The discriminating something in the hundreds of thousands of Siemens. I'm talking about Siemens here, so conductance. Yeah, may have some academic aspect to it, but it sounds like in some camps that could be pretty useful. And of course, size is a factor here too. So the bigger conductors have more of these difficult EM problems attached. So perhaps we're starting to talking about discriminating size as well as conductivity and conductancy.
So that's an interesting comment, right? Because Dennis, in your summary that you wrote, you're mentioning that, and it has been mentioned during those talks, the penetration depth is very thin for a very high conductor. So why would the size matter? If you're only seeing the outer shell of a conductor.
Well, I'm talking there about the size in think
horizontal distance.
Yeah. So that affects the EM behaviour considerably.
Could I make a comment? I enjoyed Ben's talk, and particularly one of his earlier slides that I can't remember exactly the quote, but it was something about coaxing a signal out of the late gate response. I thought that was an excellent quote, because that's basically my life. And you're trying to, is vibration noise, right? It's not a transform function with a squid. Of course, it's quite flat, but it's this vibration noise. And so the answer is, in effect, wait until the vibrations stop. In other words, take lots and lots of very short time readings, and then select out of those the ones where the vibrations have subsided. That is a solution to your noise graphs that you were showing.
Yeah, it's kind of a pruning exercise, and actually we've applied that in borehole surveys where you have intermittent motion, things settling with the probe and that kind of thing. You stack part of the only part of the time series, and you can get much better results by kind of high grading things. But there's always there's always that decision that's going to help a lot. But at some point, you're going to, yes, that'll flatten things to some degree. So you need to do that, and then make your spectral density plot out of those residuals that your high graded set, and then ask yourself the question: have I got there yet? And where's my sweet spot? It doesn't hurt to go through those motions and convince yourself that yeah, 0.1 hertz isn't low enough. Maybe that's the answer, but that will tell you, right? And the reason why getting the spectral density plot so useful, because it's a lot quicker than doing an ensemble of actual measurements. At 0.1 hertz, you have to get a lot of them to good standard deviations. Whereas with one, half an hour or whatever time series, you could answer those questions, like generate the whole spectrum.
Yeah, like your borehole surveys on surface, we've been doing this long enough to see it is periodic. You get bursts of noise. I don't know whether it's microseismics coming in or the wind subsides a little bit, so the tree roots aren't moving quite as much. But there's all sorts of different reasons for having periodic bursts of this vibration noise. And geomagnetic disturbances is another bugbear, right? You have to deal with all the time. But I like that idea, and I like that quote. I need to get that slide, that quote from you.
I have a question from Robbie. So in the chat here for Jim. So you've mentioned that in order to be able to really model well with forward modeling or obviously inversions, we would need basically to have very, very small cells, right? To be able to model the surface, yeah?
If you're using a voxelated solution, you can work around it by keeping track of skin depth and using sort of local 1D approximations. But most of the off-the-shelf sort of 3D software will have voxels of 10, 20, 50 meters. And those just can't actually handle inductive thickness. So you can get perfectly good solutions that match data, but that don't actually have all the physics built in. And if you have to do, say, 1 centimeter cells, you've got 1 million of them in a cubic meter. And you need a cubic kilometer.
So I guess the question, yeah, I totally agree with you. Yeah. So the question, I guess, would be more, what would be the expected artifacts or the expected danger of not being able to model those very thin conductors? Because we're obviously going to try to push the data, right? But what's going to happen?
You can't expect to match the decays properly. If you try to match decays properly, you'll probably be sticking other conductors in there that don't exist. To get the conductivity changing as a function, or to get the time constant changing as a function of time.
You'll have to increase the complexity. Right.
So you put in unnecessary complexity to try to fit that, such as making the core more conductive than the outside. So yes, I guess it's just a bit of a caveat. It's very good conductors are usually not well modeled.
Thank you. That's great. Answers the question very well. And then we have the one question I skipped. What about frequency, high power frequency systems? We talked about a lot of time domain systems, but what about the pure on time, more like an EMinar? Anyone has I don't know. Is it possible? Does it matter? Can you do anything?
I'm sorry, can you repeat that for the pure on time?
For instance, if you're using a high power frequency domain system instead of a time domain system.
Yeah, I think it's just a practicality. You've got so much voltage and current to pump in a loop, and you're going to aim it all at that one frequency, and especially with covering all these orders of magnitude and trying to discriminate weak from strong, you really need a lot of frequencies. So it's purely how do you spread you have to spread your energy out over your time of your measurement and across your spectrum at the same time. And if you did it with frequency domain, you'd have to have switching from one to the other. It's just a lot electronically more difficult.
I see. That's great. Excellent question. Any other comment? Okay, I think we're getting close to the hour and a half, so we're unfortunately going to have to stop soon. There was a question early on about the presentations. If the panelists are willing to share their presentations, that would be fantastic. I think both MTNet, Alan, and on our side BCGS would love to be able to share those. And yeah, I don't know if Dennis. Dennis or yeah.
We had that question that came in by email from somebody in Sweden. Can you read that one?
Do you have it handy? Sorry, I'm a little bit scared.
I don't have it handy. Sorry,
That's okay.
I don't think.
While I look for it, maybe do you have any comments for BCGS or KEGS that would like to just mention?
The BCGS will be having its annual general meeting next week, another Zoom meeting, and we're selecting the board and the executive, and discussing what we'll be trying to do next for next year and various meetings and so on. So everybody's welcome to come to that AGM meeting.
Thank you very much. And yeah, I guess we can ask the final question to all our panelists here. I'll just read it because it's a pretty detailed question. So it is more cost effective to measure on-time step response or 100% duty cycle because of low base frequency is not needed to get the same information as in the late off-time response. Okay, so the question is, sorry, I'm skipping quickly. What are your thoughts about this approach? Sorry, Dennis, I think I'm butchering that question here. It's too long. I'm sorry, Dennis. I wasn't prepared for that one.
It's fine. Don't worry about it.
That's all good. So thank you again, everyone, and then we'll close the session here. And Merry Christmas and be safe, everyone. Stay safe.
Thanks, everyone.
Thanks, guys.
Thanks.
Bye.
Thank you. Bye.
Bye.
That was great. I'm the last one. Bye, everybody.